All right. So let's see what people are sharing here. Hide, show responses. Cars moving in a straight line unless an extra force being smacked with a ruler was applied. Car went at constant speed. Replied to its motion sensors along the side. You had to correct the direction of the car because of the angle of the desk. Car kept constant speed, turned to the right a little bit. Meter stick kept it in line, right? Just like those nuns back in the day. Car was not straight, needed multiple adjustments, constant speed. Yeah, I went to a Catholic college for a couple of years. It was tough. There's a difference between should and ought to, and you just need to know that, all right? Car moved at a constant speed the whole time. Everybody moved their stuff out of the way. The constant relative constant speed. Car moving and had blinking lights. Notice that the buggy continued driving its own, steering off course, and moved by the meter stick. Car powered by electricity. Well, try to keep it at a low inference. Was it powered by electricity? Did you see me put batteries in that thing? Car did not go straight. Needed constant realignment. People moving stuff. Hard and correcting path. That's what I'm here for. Oh man, look at all the participation. Drove smoothly. Car did not. Let's see. Had to tap it back in a straight line. All right. So if we kind of like summarize, hide responses. We kind of summarize there. What's it like a car that like doesn't go in a straight line? What does it say? Right, like it pulls to the right or something. Okay, never heard that term before. So car kind of pulls to the right. Might need some realignment. Hello. Love the technology. Okay, car pulls to the right. Okay, taps to correct. Okay, if you noticed, I was tapping to correct. I wasn't smacking it. So when this is you, it's gentle taps. Okay, little love taps. More than a few people notice. What about its motion? Moving consistent or constant. We kind of saw that. Okay, constant speed was the claim. Okay, that's a simple enough word that I'll allow. Don't try to use unnecessarily fancy words here, people, right? Constant speed, that gets a point across. What else was common? Those are kind of the biggies, right? Okay, we don't need to prolong this too much. So that's the what did you notice? What I'm going to ask you now is what can, I better write it out because we don't know what it is. Boop, boop. All right, it's this. What can we measure directly? Okay, now what is this related to? Related to this claim of constant speed, right? We talked about argumentation with evidence. So if you're going to argue that the speed is constant or make that claim, what's the evidence that would support that? What can you measure directly? And here's where measure directly is important, right? You don't always hear what I'm saying. You hear what, I don't know how to phrase that properly. There's a filter there. And sometimes what I'm saying gets reinterpreted, okay? Like I said for the groups to measure circumference and diameter, but in one of the classes, they measured diameter and then calculated the circumference, which was going to pretty much make sure that their slope on their graph was pi for those circles. That's not what I was aiming for there, okay? So hear me, don't calculate anything. What can we measure directly to gauge whether or not the speed is constant, okay? Run that by the pear deck. Wow, you are already. Look at you. People are drawing graphs in a pear deck? Nope, that's a cat. And friends, I'm talking specific to this claim here of constant speed. What direct measurements are going to enable you to make that claim or to disprove that claim? And again, I can see what you're putting in, but I will project it anonymously. All right. So speed, distance traveled, time traveled, how long car took to get to a spot, centimeters per minute, timing and measuring distance, speed of the car, speed, angle, change of angle, how long it takes to go a meter, far it travels in a certain amount of time. Okay, now here, like if you're talking about a map function, this is calculate, right? Divide would be calculate, okay? Time and distance, right? So a lot of people are saying speed, but this is what I'm getting at by direct measurement. You're going to measure speed directly? What type of apparatus is involved in that? Direct measurement. What do they call those? Speed guns, right? Are any of you the U Heights Police Department? Your cell phone is equipped with a radar gun. You probably don't want it in your hip pocket. Bad things to you. Reproductive. There were a lot of lawsuits about that back in the 80s. Go check it out on the internet. So, where's a cop going to set his radar gun when he's eating his donut? So, speed, maybe not measuring that directly. Okay. Distance, time, we can measure those things directly. Yeah. Okay. So, I want to talk a little bit about that, and I want to lay the ground for something really specific in the way that we're going to measure distance, because we're not going to measure distance. Okay, we're going to do it a little bit more physicsy. Okay. And hey, by the way, I'll come back to this in a second. AP Physics. Come on, man. All right. I got a couple of videos for you to watch. If I get there. And they'd be better with sound, but such is the projection capabilities in here. This is the prequel to Snakes on a Plane. This is Ducks on an Escalator. All right. So my question to you, I wanted to pause it before the bloodbath ensues. So my question to you over on the pear deck is, are the ducks moving? So just go over to the pear deck and answer that real quick. Are the ducks moving? Are the ducks moving? Should be a yes/no answer, right? On the pear deck. There's no room for nuance here, ma'am. It's a yes/no answer. All right. And the problem with participatory democracy is we can't trust you to choose wisely here. So 22 people think yes, 2 people think no. Okay. One person was bold enough to look me in the eyes and out loud ask, "In what sense?" In what sense? Okay. So I'm going to throw that back at you now. So take a look at this and have a conversation with your neighbor. In what sense are they moving? In what sense are they not moving? All right. So give me that in a tweet. In what sense are they not moving? In what sense are they not moving? Tweet it at me, bro. I want to increase my tweets. My following. I want to get Twitter verified by the end of the year.
Start a vlog.
What?
Like a vlog of this AP Physics teacher.
Some of you are trying to sound sciencey. All right, so some selective response. They're not moving past that spot on the escalator. Okay, their position is not changing. They're moving forward, but the escalator continuously takes them back. Oh, it's like when my mom's like texting me. Okay, so, but the escalator continuously takes them back, right? They're not changing position. So they're not moving relative to the people that are filming it, right? That's why they're just standing there holding their cameras. Relative to the mall, they're not changing position, okay? In what sense are they moving? Again, keep them short, right? You don't need to throw a lot at me here. In what sense are they moving? I wish Chromebook scrolling didn't suck. There we go. Okay, so here's a few different statements on that. So they move up the steps as the steps move down. Okay, they're moving relative to the floor underneath them. They're physically attempting to go up the escalator. Okay, so they're like, you know, you do this at Shields sometimes when you get bored. You just go up the down escalator just for kicks, right? Because you want that extra little bit of fitness, up your step count on your Fitbit, that sort of thing. Okay, relative to the mall and the people not moving, relative to the floor beneath them, the escalator, the steps, as it were. Yeah, they're moving. Okay. Here's another video I made of my dad at work. Whoa, what did I just do there? Okay. And I won't make you type it in, but similar type question. So in what sense is my dad moving, and in what sense is he not moving? Just have that conversation with your neighbor. We don't need to type that in. Right? Life goals. Right? So we can just do the out loud version here. So in what sense is he moving? Yeah? He's moving to a different, like physically, he's moving across there, right? He's able to clean the glass because he's moving along there. In what way is he not moving? Yeah?
His body is not physically moving himself, like his muscles are not working.
Standing still. Yeah, you're like standing still, and then the moving sidewalk is moving along there. Okay? So what I'm trying to establish is this understanding that all motion is relative. Okay, so whether moving or not moving, it all depends on the frame of reference that we're establishing there for it. All motion is relative. The rest of that is there is no such thing as absolute rest. Like absolute zero. Absolute rest. There's nowhere in the universe that we can claim is at rest. Okay, it's all in motion relative to everything else. So motion is a relative concept. That's one of Einstein's postulates of relativity. Okay, that's kind of the fundamental thing that it gets at. So it's incumbent on us then to establish a frame of reference when we're discussing motion, and typically that frame of reference is the room. So that's why those ducks aren't moving, but they are, because they're just staying in place relative to the room. That's why that guy is moving, but he isn't, because relative to the room, to the camera people, he's moving from left to right there, okay? So a frame of reference in here is going to be a number line. And so you think about what's on a number line. Well, what's in the middle of a number line? 0, yeah? I just drew it because it was in my mind there. Should have waited for you. I'm sorry, I blurted. All right, I'll credit you with that one. All right, and then I guess I need to make the case as to why we use the number line. So let's do this real quick. All right, so back row. I want you to watch what I do here, okay? Front row. I want you to watch what I do here, okay? All right, back row. What I do? Okay, say more about it. I walk. We got the back row. You're in the middle. Chill out. Come on, back row. It's your time to shine. Walk to the right. I what? Walk to the right. Okay, cool. Thank you. Front row. What did I just do there?
You walk to the left.
Bro, what? How did I do 2 things at once? Oh my gosh! It's like right and left are not sufficient descriptors of motion here because they're based on your perspective. So, sorry, should have talked about that first. That's why I am establishing the number line as a preferred reference frame for describing motion. So here's 0. If I go, now I'm like cautious about saying right and left, but if I go this side of 0, the numbers are going to do what? Go ahead and you can draw this in your notebook, right? Do you have notebooks? Is that still a thing? Okay. So I'm going to have some numbers, yeah? Okay, 0, 1, 2, 3, 4, 5, 6. And then on the other side of it, I'm going to have some numbers, 0, 1, 2, 3, 4, 5, 6. Okay? But to make these distinct, on this side, I'm going to add in pluses. And on this side, I'm adding in minuses. And then we can make the motion distinct. So imagine I transpose this onto the floor here. And we repeat that activity. And here I go. Nobody said swaggy. I was kind of disappointed in that. Okay. But back row, describe my motion there. I walked. Go, okay. Front row. We're using that number line. I walked positive, yeah? Okay, if that number line's on the floor there, I walked in the positive direction. Negative, if you're having trouble remembering, is towards City High, okay? Positive is towards the landfill, relatively speaking. Okay, so there's our number line. And one of the words that a few people used in their descriptions of the ducks that I saw was position, okay? And position in here is preferred to distance, and I'm going to kind of state, I'm going to support that claim here in a second. So we talk about my position, so, bro. Oh, I saw it, I switched it to green. There we go. Person, okay, that's as good as it gets. And this person is at a distance of 3 meters from 0, or the origin. That's sometimes the verbiage for that. This person is also at a distance of 3 meters from 0. Okay, so that's when we're talking about distance. Distance only wants to know how far. So distance for both is the same. But then if we talk about it in terms of position, positive 3 meters. Position of this person, what? Negative 3 meters, okay? And then, like, I can do it more efficiently, right? Just by adding in this sign convention here, now I can convey more information in a more efficient way, all right? So that's when we're talking about position. But that's boring if things are just out of position. If we want to look at a change in position, let's say the person starts here. We'll call this P1, and then they move to here. We call this P2, okay? There's a change in position that occurs. Bruh. What?
That's right.
That's about as clear as my normal penmanship, but let me try this again. Physics is great. We watched Mr. Harding struggle with technology today. Again. Change in position. So I'm just going to take P2 minus P1, okay? Later position minus earlier position. So mathematically, that's going to be -3 minus -3 meters, I should say, minus 3 meters. Who's got a calculator handy? Thank you. -6 meters is the change in position, okay? If we had gone the other direction, and let's do that in some other exciting color, ooh, yellow, okay? If this is P1, and I move this way to P2, then that, and again, physicists, very lazy, don't like to write because, well, damn it, the technology sucks. So instead of changing, we're just going to put a triangle there, delta, and that represents the same thing. So change in position here, yellow P2 minus yellow P1. I'm going to have P2, that's +3, minus P1, that was -3. Who's got a calculator handy? +6 meters, okay? So it's conveying not just how far, but also the direction of it, okay? That's why it's preferable. It conveys more information in a very tight package. The fancy pants word for this, okay, pinkies out, is and again, it's a fancy word, so you have to displacement, okay? So can we practice that quick? This is how we do it in ELL. Repeat after me. Displacement. Try that again. Your pinkies were out. Displacement. Fantastic. Okay, you guys are going to go to some elite prep schools. This is going to be great. All right. So with the buggies, that was a long walk to get back to with the buggies. We're going to be checking out what relationship, if any, exists between position and time. Okay? If I want you to measure position, I can't just give you meter sticks. What do I need to give you? Well, I need to give you timers, but if I want position, what did I just establish? If we want position, we need origin, which is located on a, begins with underline. Now I need to give you a number line, okay? So, let me do that for you here. Just a second. Fortunately, I had hidden my number line for myself, but so yep. And then Daniel, if you can hold that for me. Did they not have a combo for? No. I'm sorry, I had one in the box. Let me know. All right. Lady. Just gonna overlap these bits like that. Yeah. No. Like that. Perfect. Okay. Yeah. So like 0 times.
Yes.
Yeah. That's
How is this easier than right here?
right here. Trust me, I applaud your line of thinking. All right, so here's 0, and then we hold down here. Hey, Fred, what do you notice all those numbers if we go that way? Okay, you do that, but what do you notice about all these numbers? Dude, I'm way too all these damn things. Come on, okay? And the numbers going this way? Positive. I didn't put plus on because it's just a third, right? Okay, cool. So physicists are lazy. That's all good. So here's our number line. Or, yeah. It's our number line. So we can measure position, okay? Now, we got to talk about, I'm getting fast because I'm not sure when we're out of here, and that makes me nervous. Let me check. That would be the smart play. 31. Where are we relative to that?
25.
Oh, we got this. Okay. Is the speed constant? Okay. So, yes. Well, we got to measure some stuff. Let me show you a couple of clip things here. This is like on the front end of our canvas. Blah, 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 blah. Which one of these is canvas? None of those is canvas? Hang in there, Chucky. That's not canvas. He got bogged down when he couldn't find canvas. There we go. I knew it was somewhere. All right. Boop. Like the freaking thing on the front end of canvas, right? How do I get back to it? Dashboard. There we go. Whoop. That thing, right? I figure I got to pay for these kids and they're damned expensive. I'm going to like use them for my bidding. So this is Charlie Harding running through Willow Creek Park, and I'm using an app called Motion Shot. Okay. How constant is his motion? Run that by your neighbor real quick. This is not the first take. Let me just put it that way, okay? This kid sucks at running, and we worked on it. And to what extent does that look like constant speed? You run that by your neighbor real quick. Okay, now compare and contrast. This is like I'm fortunate that my kids are still at the age that like our vacation can just be Mercer Park. Okay, so compare that to this is Cora on the swing over there, the little daredevil. What do you notice about her? Oh, you can't see it. The damn thing. Let me de-brighten the room.
I think if you take off the color things, you know how it's kind of red?
How do I make that happen?
You have to go to the editing position of it and turn it off. It's not that hard.
Okay. Can you see that ish? Kind of. Like, what do you notice there? Yeah, like the gaps are changing. Yeah. Okay. Compare and contrast that to, compare and contrast that to this one. Okay. Can we kind of visually see if the speed is constant or not? Right. So they used to call that like stroboscopic photographs. Okay. There's like a really famous series, and some of them are nudes. So I'm taking a little bit of a risk here. Stroboscopic motion photo. Images. These are more modern, okay? Right? Oop, yep, nudes. Don't Google search it, all right? So, right, so it's an interesting way of capturing motion and gauging how I gotta like find a safe one to stop on. Okay, there we go. Let's go away from that. It's a reasonable way to gauge the constancy of the motion. So the way that we have to okay. So I'm going to share with you a process that I'm going to ask you to use. Thank you. So I brought that for figuring out the constancy of this motion here. Okay. And gosh, we need somebody with a stopwatch. It's got like a stopwatch. So secure. If we read that slip in one class, then it's just, oh my God, no. Then you're just chanting, drawing Pepe. See, exactly. Now the chant is back. Yep. See, so that was okay. Okay, Mr. Neutral's idea was that you should. Well, we'll stay away from this. That's not it. Okay. Cool. You got me timing? All right. So we're starting at a position of -5 meters. Okay. 3, 2, 1, go. I forgot the meters there.
No, you can do it.
And stop. 12.82, aka 13 seconds. Okay, so hey. We just went from -5 meters to 0 meters with our displacement. Oh, sorry. What's our displacement?
5. 5 centimeters. Positive.
Positive 5 meters, yeah? We went positive 5 meters in 12 seconds. Is that enough information to tell us that it was constant speed? No. Okay? So instead, what I'm going to ask you to do is do like a low-budget version of the stroboscopic photo. You're going to need to take some of this masking tape. Come on, friend. Okay? And just like tear. And I think on my camera, it puts a marker and takes a picture like every 10th of a second. I am not that fast. Okay? I only had one thing of coffee today. So how often do we want to put a marker down? Every, what do you think?
2 seconds.
10th of a second?
Yeah, 10 seconds.
10 seconds? Well, it took 13 seconds to get there. What seems like a reasonable way to break this down to get 7 data points?
1 second.
Every 2 seconds, we'll try it. Let's see what happens. Okay. Ooh, now I need to mark my initial position with the -5 meter mark. All right. You might move that pen for me. Okay. And we're going to give you a 3, 2, 1, go, and then call it every 2 seconds. Okay. Ready? 3. Say now.
Okay, go.
Wait, yeah, let me know. Ready? 3, 2, 1, go.
Now. 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 Now.
All right. So everybody kind of like stand up and look at this. Compare and contrast that to the kid on the swing and the kid running. What's the foot more like?
Kid running.
Kid running. Okay. We look at it.
Yeah, that's fine.
Reaction.
Okay. So this is our process of laying down breadcrumbs. Now the really important part of this is when you're done with it. So -5 meters, -4.02, -3.08, -2.35, -1.6, -0.9 meters. Okay. Position. I'm not reading this. Ooh, and the last one, probably like -0.1 or something. Okay. I'm reading position. I'm not reading distance travel. You understand the difference here? Where is that on the number line? Okay. So tomorrow when you get to class, you and your friend are getting a buggy. Now, look over there. What do you notice about the buggies? You know what I'm saying? Watch this. Watch this.
No,
I'm on the luck. Okay, awesome.
Okay, what do you notice about this one? Okay, so your group is going to have a partner group. Okay, shush, because this is kind of the really important part to know what's going on. Okay, it's like soccer. Do you ever notice that? Like soccer teams are either blue or red. So you're going to have a rivalry match. You need to be, if you're a blue buggy group, you got to find, if you're Everton, you need to find your Liverpool. Okay, if you're City, you need your United. So you have a blue, if you're Chelsea, then you need to find a different team. Okay, so you got Arsenal. Okay, you got Arsenal. So, okay, you smell me? So you're a 2-person group, and you're a blue buggy. You need to have a friendly 2-person group with a red buggy. Friendly buggy. Okay? Because we're going to do some stuff with this, right? Remember how we talked about verification happens best by like predicting and then checking to see if your predictions work out? We're going to do some of that in the club. That's going to be Friday. We have class Friday, yeah? Steve. All right. Ooh, oh, thank you. This is the other important thing. So that the janitors stay on our side. Now, the other physics teachers suck at this. I know this because I constantly get emails. Hey, yeah, I used to do it. Pick up your tape when you're done. Okay? Both the measuring tape and the tape tape. So, Emmanuel, if you're on that end, if you can wind that up, we'll do it like, what's that movie, Lady in the Tramp style?
Whatever the cleanup I serve.
Oh, I like tomorrow. Yeah, I'll be fine.